The last topic we're going to cover in Flexure is design of one-way slabs. So for slab design, let's first talk about what a slab does. So here I'll draw a slab. There we go. And let's see, that slab is sitting on some beams like this. So first of all, there we go. First of all, this slab is the floor. So you put a load there, and the slab resists that load. It's a floor over the beams. But a slab, and so this slab will transfer this load. It'll bend like that, and then transfer that load down to these beams. But a slab is also a diaphragm. So so let's say you have a building that looks like this. So let's say you have a frame there, and you have 3 of these frames. So there, and, and so on top of that, you have a slab. Okay? So like this. So you have a slab down there. Okay, so you have a slab like that. Okay, and when you put a wind load on your building like this, and you have some kind of cladding like this, that wind load blowing onto the cladding is going to be resisted by the diaphragms, the slabs. And so if I draw the side view of that, okay, so I'll draw a side view of that. There we go. And you have this wind load coming onto the building. And it's going on to this cladding. These 2 slabs, they're resisting that like a diaphragm. And if you now look at the top view of the diaphragm, so there we go. Oh well. Okay, so you have that, and you'll have this load on the edge of the front edge of the slab. So that load is like right here. Okay. It's being resisted by these 3 frames. Okay. And so that load is going into these frames. Okay. So those frames could be shear walls, brace frames, moment frames, but it transfers this lateral load into the vertical lateral elements. So a slab can be a floor to resist gravity loads. It's also a diaphragm to transfer lateral loads to your lateral resisting system. Next, I want to talk about one-way versus two-way slabs. So in this first instance, we have a one-way slab. And when you load up this slab, the slab will bend this way. Okay? So if you were to look at it like this, and there's your slab. So this slab is bending this way. Okay, okay, so let me color that in. bending like that. So the slab is only bending in this direction. However, if you had a slab supported on all four sides like this, and it's square shaped, it's not a narrow rectangle, it will bend in both directions. It'll bend across this way, and it'll bend across this way. So you can think of the one-way slab as sort of like a stretcher. So you carry that, and then it'll sag like this with the person on there. Okay, and so that's a one-way slab. And you can think of a two-way slab as sort of like a trampoline. And so, you know, you would have springs over there. If you ever jumped on a trampoline, and it will look like this. And so when you jump up and down on a trampoline, the trampoline sags in both directions. Okay, so that's a one-way slab versus a two-way slab. In this class, we're only going to talk about one-way slabs. So the one-way slab design is a little different than what we do for beam design. In a one-way slab, we're just going to design 1 foot wide. Okay, so if you look at this picture here, we're going to design this 1 foot wide section because every foot along this length of the slab is the same. So instead of designing 60 feet of that slab, we'll just design 1 foot of it and repeat it all the way across. So we're going to design a 1 foot wide section of the slab. And so remember that the beams supporting it are this way. So it's bending this way. So it means the main flexural steel is going this way in the slab, okay? So what we're going to do is we're first going to choose the thickness of the slab based on rules of thumb. Once we have the thickness, then we're going to just design it like a rectangular beam, but with B equals 12 inches. And we'll get the moment. And after we get the moment, we'll get RN, then rho, then AS, just like we've been doing. We'll choose a steel. And we'll remember that the steel goes in the direction of the bending of the one-way slab. However, in the perpendicular direction, so in here, let me put that in green. In this direction, okay, it can still crack. It can shrink, there can be temperature change. So even though our main steel, so let me draw the main steel in purple. So even though the main steel is going this way, we still need steel, even though it's not bending this way, we still need steel this way, perpendicular to that, to control cracking and shrinkage, to control temperature and shrinkage. Cracking due to temperature and shrinkage, sorry. Okay, so that's what we're gonna do. And so the first thing we're gonna do is pick the slab thickness. And we're just gonna use these rules of thumb from ACI. And so an interior span, so these are all interior spans here. The thickness of an interior span is L over 28, the minimum thickness. And on this last exterior span, the minimum thickness is L over 24. Now, really, we probably only want one slab thickness throughout. So what we'll do is we'll calculate L over 24 for the outside, L over 28 for all the interior spans, and take the biggest thickness. In this case, it's a little weird. Usually the outside span has a shorter span because it's L over 24. But because of this stairwell here, that first slab is actually the widest one in this particular example. Next, we need to get the moments. So let's go back to the procedure. So first we got the thickness by L over 24 and L over 28. Next, we're gonna choose the steel. And if you remember how we've been doing this, if you know the moment, you can get Rn, and from Rn, you can get rho, and from rho, you can get the area of steel. And so we're gonna have to know the moment on the slab. It's highly indeterminate. And so what we're gonna do is use these approximate ACI moments, and these formulae use clear span lengths. So I think I'll stop here and make the next video talk just about these approximate ACI moments.